Good. On to this webinar from the Open Group, which today is being brought to us by Evolution. Speaker today is Ed Granger. Before I hand over to Ed, I'd just like to go a few housekeeping issues to keep the event moving forward smoothly. Firstly, with regards to questions, and of course we would encourage you to submit questions. The best way to do that is if you write your question in the text Q&A facility. If you put a question in there, can I ask you to address it to all participants? That way one gets to see all the questions that are being submitted. And the is to try and answer as many questions at the end of Ed's presentation today. They're also being fully recorded. So if for any reason you have to leave early, or if you experience any local technical difficulties, I know that sometimes the audio can be a little problematical in various geographies. The one who has registered for today's event will get an email with a link to that webinar recording. Ed, if you're ready, can I ask you to start presentation today?
Yep. Okay. Thank you, Simon. So yeah, and thanks everybody for taking time out of your day to listen to this webinar. We'll be sort of taking you through the basics of what we mean by enterprise architecture algorithms. I think before we dive into the content, I just want to start with some introductions. It's all about me and also about Evolution. So my name is Ranger, I'm a consultant specialist with Evolution, and prior to joining Evolution, I worked for about 10 years as an enterprise architect, primarily in financial services. So actually, we're a relatively small company. We have one major product, or I say line of products, which is our Abacus enterprise architecture tool. I think many of you may have heard of that, and I think many of you probably are using it. It's also saying that historically Evolution is a spin-off of the University of Technology in Sydney, and we still have links with that institution. Infographic on screen gives you just some sort of key facts and figures about the company. I'm not going to read them out one by one, but I mean, I think the only thing I would ask you to take away from this is that we have quite a diverse client base. We have customers in every geography, and we have customers in all kinds of different industry sectors. So we get to see the kind of challenges and the kind of demands placed on enterprise architecture practices across the world. Important to stress that when we're talking about enterprise architecture algorithms, what I'm going to present to you is very much Evolution's view of what EA algorithms are. We know other people working in space, and I'll let them represent their own work. But we're going to give you our personal view of what we mean by these algorithms. It's worth pointing out that actually Abacus, was actually built around the concept of algorithms. So the acronym stands for Algorithm-Based Analysis of Complex Systems. So I don't know where it comes from, but I guess it reads better. So algorithms have been built into the product from day one. But no matter how much my pre-sales team might like me to, I'm not actually here to sell you the product today. So we're going to take a broader view at how we've implemented enterprise architecture algorithms. To do that, to a certain extent, I do actually have to show you some features of the tool, or at least talk you through how they work, because our interpretation of the problem is what we've implemented in our product. But I want to show that that's a broader context, really. So what EA algorithms are, what we mean by enterprise architecture algorithms. We're going to tell how they work. Now, obviously, we're not going to tell you exactly how they work, because that would be giving away IP, but we're going to tell you in broad terms how enterprise architecture algorithms work. Most importantly, we're going to show you how you can use these algorithms to deliver EA value. But the majority of what I'm going to present to you is actually what we're doing right now with customers. There's a bit of strategy in there, so we've tried to put it in about where we see the market going and where we see the capability going. Most of what we're doing and most of what I'm covering is actually what we're doing at the moment. So let's start with a kind of 50,000 feet view. Let's start with a top-down view of algorithms and how they kind of relate to EA's core mission. It won't be news to anybody on this call that algorithms are hot property. The concept of algorithm is nothing new. It's been around well before the dawn of computing, and even computer programs are just algorithms in a sense. So why are algorithms like hot property now? Well, it doesn't take a rocket scientist to figure out out that it's down to the kind of companies we have on the right of the screen. So these are the companies that have taken algorithms and monetized them, and use them to disrupt traditional business models. And then that algorithms themselves have now almost become part of that digital brand. So we may not understand how they work, but we understand at some level that this is the kind of a secret source. Algorithms are like the alchemy that help, convert the base data into money. And what's in that is really, the amount of data that we capture out of our day-to-day lives now and our business. And this is driven by our interaction with those digital services. This is obviously driven by the proliferation of processing devices, mobile devices, wearables, the Internet of Things. But key point in mind about algorithms is that the value generate come continuous feedback. So that we're continually exposing information to these algorithms about our browsing habits, viewing habits, our shopping habits, mean that they are continually refining the intelligence they create about us. So relate to the world of architecture, because I think in the past, algorithms were kind of off the architecture radar. Architecture used to be about the boxing lines, and off big boxes, so it would be about the new data center or the new operating model or new ERP platform. And to a certain extent, algorithms were an implementation level concern. So this was specification, this is detail. On the previous slide that algorithms are now well and truly on the radar of architects. Just for the effect they're having on the business models, they're also forcing us to adopt new technologies, and we're having to do things like embed analytics and frontline decisioning. We're having to expose also decisions as services to our business partners. But another sort of dimension, the kind of traditional backstop, traditional kind of risk and governance role that EA plays. On the hand, algorithms are very valuable intellectual property, and we have to protect that, and we have to certainly, to a certain extent, mask that from theft. The other extreme, we have things like regulators, market regulators, who want increased transparency of our operations, which includes automated decisions. So these are slightly in tension, and that's something that architects, through governance processes and through risk management processes, potentially have to measure. But as architecture, can be in a slightly strange place, because we spend our days obviously, working with high technology, evangelizing high technology, promoting high technology, and yet the practice of EA itself often isn't particularly automated. So, when we talk about EA algorithms, it can seem like a slightly alien concept. And a lot of people ask, well, can actually enterprise architecture itself algorithmic? Well, it is, and to demonstrate, I wouldn't necessarily say evolution of betting the farm on it, but I think we are strongly convinced the algorithmic content of EA, the practice of EA, is only going to increase in the next few years. So how about applying algorithms to enterprise architecture? Now, there are many ways to actually, simulate or show the process of EA. And best known of those is TOGAF's architecture development method, the ADM, which I'm thinking many of you are very familiar with. Now, Evolution, we support frameworks, we support many modeling standards. So we kind of abstract, process up a level. And EA basically consists of two primary activities, and that is modeling and analyzing. And we do it in an iterative way. So regardless of where we are, working with a current state view or a state view or any number of transition views, going through that loop of modeling and analyzing, continuously. And we're a data-driven company, we see the visualization or the presentation of that modeling and that analysis as being actually something which is obviously related, but separate activity. Now, thankfully, it isn't a closed system. It has inputs, it has outputs. So, from the point of view of inputs, we obviously need to discover and understand our landscapes. We need to understand our existing business processes, our existing technologies and applications. We need to understand the organizational drivers and objectives which are actually pushing us to do architecture in the first place. and have outputs. Our product as enterprise, we have to make recommendations. We have to produce roadmaps and target architectures. And this is how we inform, how we deliver the architecture that will actually align to that strategy. So algorithms playing in this space. Well, we see them playing in those three activities of modeling, analyzing, and visualizing. And I'm going to through some examples of three of those. But I actually want to talk about how it is we can talk about EA algorithms at all. So what is it, that's changed? That means we can talk about algorithms in the enterprise architecture space. Two macro level trends I ask you to consider. Now, you may or may not agree with this, but I certainly think they're worthy of consideration. And please excuse my use of buzzwords here, but I couldn't think of a better word. The first is what I call the datafication of the enterprise. This is a trend that we're certainly seeing is our way of understanding our enterprise is moving from something which is primarily content driven, in other words, project documents, Word documents, Visios, to something which is much more data driven. What I mean is if you think of an EA framework like TOGAF or maybe like Zachman, you have each of the domains of that architecture, your business, your information, your application. These represent almost like pots or buckets that you have to fill up with information about your enterprise. You actually have to build that information asset. Seeing as more and more of that information is available from the feeds, structured data. So it's coming from sources. It's coming from, the traditional big rock enterprise repositories, so things like our CMDBs, our EOs like Abacus, some things like our supplier relationship management tools, our project portfolio management tools. These are very useful sources of information. We have, discovery tools, network discovery tools, application discovery tools, and we have, things like ETL tools, analysis tools which produce rich seams of metadata. And increasingly, new practices or recent practices in software development and hosting, like ops, is driving infrastructure as code. Cloud means you can often now consume a view of your infrastructure as a data feed or as an API. And also, it's not all the physically implemented enterprise. It's also, as architects, we have to think about things like reference models, and we have to think about things like standards. So, you might have your own, for example, high-level business capability model or business function model, or you use, an existing standard. Like if you're in banking, you might use BIAN. If you're in insurance, you might use Accord. If you're in tax, you might use ETOM. All these are available as data. Our technology standards, there are sites out there like Technopedia, which will enable you to consume via APIs long lists of standard market, off-the-shelf software technologies. From the organizational point of view, we have things like HR systems, identity management systems, and even social networks like LinkedIn that give you the people in the architecture domain. So I guess the bottom line really is that the enterprise's business and technology model is increasingly becoming machine processable. Now, with that, I guess the other macro level theme, and I guess is what I would call the datafication of enterprise architecture itself. Now, I'm an architect by background, kind of know that just having lots of data doesn't necessarily give you value. You actually have to either gather or impose some kind of structure on that information in order to create value from it. As architecture itself has kind of got better at managing its own information, it's actually evolved at managing its information. So EA teams, they might start off as a practice. It's a very consulting type model where you have roles, you have guidelines, you probably have some best practice. Now over time, that becomes codified, as work like TOGAF or like Zachman. So you actually start to define, repeatable processes and potential artifacts that inform how you're going to do enterprise architecture. What seems to be happening is that, EA teams and EA organizations find that they need to structure that data. They need to structure the data that underpins those artifacts. and they need to come up with a formal definition of each of those areas of data are and how they relate to each other. It gives rise to the meta model. So I think meta is a bit of an image problem. Sometimes you can think of a meta model as what happens when you give an EA framework to a data architect. But a meta model is a hugely powerful asset. Because something that, going back to the previous slide, it's a structure that gives you the ability to create an integrated view of your organization. And that's tremendously powerful. Now, because we support multiple frameworks, we support multiple modeling standards, we say, well, what's even more fundamental than the meta model? What's the structure behind the structure? As it were, almost like the fundamental particles that make up the enterprise. For us, that graph. So it's working what we mean by a graph. Now, there are some very mathematical purist definitions. I'm going to use a less purist definition. But fundamentally, a graph is a data structure that classifies information into either nodes or components, edges or connections. So solution, we call them component connections. It's a slightly more user-friendly, slightly more architectural way of describing it. But basically, to give you an example, if you're the things that we are most interested in as architects, whether we're business architects or application architects or whatever, this is the things, the actual objects we're interested in modeling are generally components. So there could be applications, there could be servers, there might be organizational units, there might be processes. And then the connections are the way that we understand the interrelationships between those components. So, for example, an application, which is a component, is hosted on, which is a connection, the server, which is a component, or a business component, depend or users, connection, and application. So it's a full and very fundamental and very powerful way of modeling, regardless, of which architecture domain you're working in, of modeling those kind of elements and their interrelationships. Now, both components and connections can have properties. So application, for example, might have the date on which it was commissioned, or the date is planned to be decommissioned. The server might have an IP address. But even connections can have properties as well. So a connection might represent an interface between two applications. It might have some properties describing, whether that's a unidirectional or bidirectional interface, or whether it's using HTTP or HTTPS, etc. So graph one, they're very good at representing complex systems like enterprises. Flexible, so they're very easy to extend for new sources of data. They're very easy to scale, and they also can be very performant for the type of queries that architects tend to want to ask, which is the kind of what's connected to what query. If I mention the server, which applications are likely to be impacted. But spending some time covering graphs is because the algorithms that we build and we run virtually all leverage this graph structure. To understand how they work, you have to understand the fundamentals of a graph. So let's look at what those categories of algorithms are. We subdivide or would categorize our algorithms, 4 ways, but they all have the common property that they're defined by how they process an enterprise graph. So we have to process the properties of components and connections. In other words, to create or update properties of those components and connections. And these are the algorithms we use for analysis, or analyzing the architecture. We have algorithms that actually process those components and connections themselves, the structure of the graph. These are algorithms we'd use for modeling. And algorithms that will actually create views of the components, connections, or properties. These are used for presentation. And we have, and I'm going to disappoint you here because I'm not going to cover these in any detail, but we have algorithms that actually will work on entire architectures, which is a collection of components and connections. And these algorithms we use to actually create roadmaps, potentially different points in time. I have a white paper about road mapping that covers some of this, and if you want to see that, then please drop us a line of the details at the end of the webinar, and we'll just send that to you. Just looking at the type of algorithms we use to actually analyze our architecture. But before that, I want to just step up a level because we kind of talked about graphs, we talked about algorithms. This is all very kind of it's very cool, but also very conceptual. And we have to think about the business context of this. In fundamental terms, when we're talking about analyzing an architecture, we're talking about being able to answer some of those hard questions that the business will ask about our roadmaps or our target architectures. So architects are broadly speaking expect to answer for how their architectures will perform. What I mean by this is you might be presenting your architecture to a set of business stakeholders. And in my experience, and I've been in a few meetings like this, business stakeholders are very good at asking very simple and very hard questions, like how much is it going to cost to run? Or, will it scale? If I bring new business through the door, is the architecture going to scale to support that? If service has been poor, is it going to be available when I need it? Now, these questions, but they're actually pretty tough to answer. And no matter how experienced you are as an architect, often, experience will only take you so far because, each architecture requirement is different and the business and technical landscape is continually changing. How do you go about measuring or analyzing the performance of an architecture? Then at least the theory is straightforward. So assume, if you're doing architecture, that you have a set of organizational objectives, the things driving the architecture effort in the first place. You're modeling the architecture, regardless of which, whether you're working in business architecture or application architecture or technology architecture, you model it at a point in time. Two is we then take some properties of that architecture, cost or service availability or performance, throughput, and we aggregate them up to be of measures and metrics. Now, for every point in time that we model the architecture, so we can aggregate up those performance measures and understand in broad terms how that architecture is performing and whether or not it's getting closer or further from those organizational objectives. Now, in very crude terms and very high-level terms, demonstrate that roadmaps are aligned to objectives. Now, simple. Doing it, measuring architecture performance is really hard, and this is because the enterprise is very complex. It's made up of a whole bunch of it's made up of various number of moving parts. Those parts are highly interconnected, and a property of complex systems is that it's what we call linear. It means that you can't always predict what the result will be for a given set of inputs. So it's to a certain extent hard to predict how the architecture will behave. That's because those performance measures are determined as much by the interdependencies between the elements as by the elements themselves. And this is where a lot of traditional analysis kind of falls down because it tends to abstract out the performance of each measure or of the element or each part of the architecture from its context. You might look at, for example, the cost of infrastructure in isolation or the application in isolation without understanding how the costs are influenced by the other layers of the architecture. It can lead to misleading results. It can lead to massive underestimation of the impacts of doing a piece of work. It can, lead to, misidentifying benefits potentially. So the algorithms work a holistic way, and the way they work is, regardless of which element we're looking at, they work by understanding how its performance is affected by those it's connected to. And this is what enables us to understand how things like financial qualities like cost or non-functional qualities like service or actually ripple up from of the architecture to another. Through four of the kind of primary analysis algorithms we have, or sets of algorithms we have. And I'm going to start with the one that people always want to start with, which is the money. So understanding how cost is transmitted through your architecture. We have a set of algorithms which we call our financial algorithms, and they allow you to actually model cost in your architecture, both from a kind of annual cost basis and also from a sort of TCO or total lifetime cost basis. And they basically model the cost using a series of standard cost properties. So they use like capital expenditure, operational expenditure properties, fixed and variable cost properties, including stuff that you can import from predefined standards. And they'll allocate that cost throughout the graph. So you can see kind of on the graphic on the right, we have locations, and these could be data centers, these could be offices. This is then allocated up to the servers in those data centers or the business units in those offices. And it can be allocated up to the application level, allocated up to the process level, and other potentially. You can allocate it up to your very high level capability views, even strategies can be costed. You know, a fixed view of cost, because cost flexes and varies over time. So what the algorithms will do is they will actually create a unique cost profile for elements in this architecture. So be it a server or an application, they can project the cost forwards based on some criteria 20 years ahead. And then actually aggregate this information. So you can understand the cost of any element in isolation, or look at a whole portfolio. So you can look at the cost of a single server, or you can look at the cost of a combined, you know, of an entire data center. Then visualize and present this cost data. I'm just showing you a few from Abacus. So, you know, we have on the left-hand side, we have a very small application portfolio, and this is a visualization of the run cost projections for applications over the course of 5 years. You can see some of them are being decommissioned, so the cost is dropping away to zero. Some are actually, you know, staying fairly steady. Some are climbing slightly as we're putting more business onto them. A couple of we have, you know, a view of costs by supplier or by business department, and these costs have actually been split down by the strategic ratings of the application, so we can see how much that cost effectively is non-strategic versus strategic. Clearly, you can aggregate your costs up to very high-level constructs like capabilities or strategies, understand, you know, effectively the costs of implementing those strategies or those high-level capabilities. Now, I think it's worth pointing out about these views is that, you know, the algorithms, all they do is produce numbers. They actually create the charts. So parsing function is quite separate. So you can consume that data into whatever your preferred means of visualizing it or presenting it is. The key bits of analysis we do is we analyze the complexity of architectures. So complexity is, you know, one of the big challenges for our teams and for businesses in general. But it's often hard to define. We actually have a very simple definition of complexity. And one in simple terms is the connectedness of each component. So to what extent each component is kind of hardwired in to the architecture. So we know the overall connectedness, and we can look at specific types of connectedness. So I've got an example here. I've got some applications. Those applications have interfaces. And in this case, we're basically rating those applications by how heavily integrated they are through interfaces with other applications. So we get those views up. And just to show you another example of the kind of analysis views we can create, sometimes the simplest views are actually the most powerful ones. So we have, you know, on the left-hand side, we have a high-level business capability map. And what we've done is we've used the algorithms, we've used the complexity algorithms to actually heat map those abilities by the underlying IT complexity and the complexity of the business processes that underpin them. It's quite an abstract concept. It's often most powerful when presented in conjunction with another performance measure. I've actually put a view of TCO, of total cost of ownership, by capabilities. So the same capabilities which are on that heat map are on the right. And so we can see, for example, that market and sell products and services, you can probably just about make that out if you squint. That accounts for, I don't know how much it is, it's probably about 12% of the overall cost. Believe from the heat map that that particular capability is an area of very high complexity. So it's likely that there might be some implication there, it might be some benefits we could go after. terms of managing impacts, the bubble chart at the kind of the bottom right-hand side is really just showing applications by number of interfaces they have. So a kind of a chart version, a chart representation of the previous slide. It's giving you an idea of where those applications are heavily integrated and where they may be therefore difficult to uncouple from the architecture. Now the analysis algorithms I want to talk you through is availability. So what by availability is service. So talking about the extent to which infrastructure or applications or processes are available when required. In measuring and the way availability algorithms work is they are concerned not so much with the availability of individual components or elements, they're concerned with the overall ability of the system to complete a specified mission. And when you run the availability simulator, is you actually want to define a mission that you want to complete. Now this could be something like a sales process. It could be taking credit card details or a credit card transaction. The thing is, can we actually successfully complete that mission? And what these will do is we'll use the Monte Carlo method, that's a stochastic, that's a random modeling method, to hundreds and hundreds of randomly generated availability scenarios. So they will literally go through the architecture, turning things off and turning them back on again according to some predefined properties. To actually see, complete this overall mission, with components. So if I lose this server, is it going to kill the process, or is it simply going to slow things down? Each component effectively is scored based on its own availability and the availability of the components that it depends on. But again, the key thing here is to analyze in a holistic way and understand the overall ability to complete the mission, not necessarily the availability of individual components. There are different ways to visualize this. I've got an example diagram here, which has been heat mapped by availability. This is a top to bottom diagram showing everything from the servers up to the applications and platform services up to the processors. And you can use charts, obviously, to represent availability. So you can, for example, show the availability of servers and then correlate that with a view of the availability of the processors they support. So the fourth standard algorithms is what we call our performance algorithms. And this is where, we're trying to answer the question, can my architecture scale? Can it support the business volumes that we need to support? So we're talking about business volumes, we're talking about, transactional throughput. We understand the extent to which the architecture, be it business architecture and processes or applications, can actually process the volume of business that's being thrown at them. In availability simulation, we use a technique here called discrete event simulation. And what this does is basically fires incoming messages at your architecture, bombards your architecture with incoming messages, and the algorithms monitor the response of those components to those incoming messages. Analysis is both component by component and end to end, and it will show, for each element in the architecture what its transaction handling volumes are, if there are bottlenecks or any queuing, and then resources are either overwhelmed by the volume of incoming messages, or underutilized. So your guys in the call center might be sitting there twiddling their thumbs with not much to do. So again, options for how we visualize this. I guess probably one of the most useful ones is the biggest chart here. It's what we call a response time chart, and in this case it's for an automated pricing process. So we have each step in the process is being rated for its response times, its minimum and maximum average response times. But the kind of yellow spark line, what that's showing is when that process step is actually required to respond by. So basically the deadline by which it's required to respond. So most process steps are actually falling well within the deadline. One or two are actually exceeding it, and those are our particular problem areas. So like for standard algorithmic simulators, now, cost or complexity or availability are actually surprisingly generic across the different domains of architecture, business, application, technology. There are some algorithms we use which are very specific to a given architecture mission or a given architecture domain. A couple of examples of this are application portfolio management algorithms and cloud readiness. Now, something like an application portfolio management algorithm looks at your application portfolio and uses a number of different criteria to rate those applications by fit, which is basically their current fit with the business operations, to the extent to which they successfully support those business operations, and so the extent to which they support business strategy. By their technical fit, so again, the equivalent, the extent to which they have good technical integrity and that they support technical strategy. And with those applications, you can then visualize them on something like this bubble chart, and you use that then to determine the investment profile for each of those applications. So you might use a 4 rating, you might use a time or item-based rating to say whether you're going to invest in these apps or decommission them or replatform them potentially. So the cloud algorithm works in a similar way. It uses slightly different criteria based on things like, from a business point of view, you can actually push that application out to the cloud. If it has sensitive information, then from a technology point of view, where the technical platform is something that can be put out to the cloud. So we're continually amazed by what our customers are doing at base. So we've seen customers repurpose these existing algorithms for entirely different uses. So, for example, we've had customers who've used our financial algorithms to actually measure heat distribution in data center power networks. It kind of reinforces the point that when you have a very generic structure like a graph, and you have generic algorithms, they're hugely flexible and hugely extensible. So it's something that we're actively putting a lot of effort into. We have a beta version at the moment, is actually the ability to self-serve, to design your own algorithms without the need for coding. You can then run across your data set. Now, everything I talked about so far has been about how you go about analyzing your architecture. So how you use algorithms to understand how your architecture is performing. So anyone who has been involved in setting up and running a CMDB or running an architecture tool will probably be thinking, yes, but at this point. Because there is, I wouldn't say it's a problem, but it's a constraint we have to be mindful of. And that is, to put it honestly, that size an architecture, you have to have an architecture. So you need a reasonably accurate and a reasonably complete view of the architecture to some of these algorithms. Now, we find often overestimate the amount of information that they need to start getting vast. So you can actually get some very useful information out, some very telling analysis out with a relatively small population of data. But nonetheless, it's challenging. It's challenging to actually get to that level of population because it requires a lot of manual effort. We can help mitigate that. One I've kind of referred to already is that we take advantage of all those streams of data. We plug into as many data sources as we can, start to build up the population of our understanding of the model and the enterprise. But the other actually use the algorithms to help accelerate that modeling process. And this is where, we come second category of algorithms are structural algorithms, and the ones that actually or manipulate components and connections instead of the properties. Do this. Well, a concept to get hold of here is what we call, in evolution, we call inference. So basically, inference is when we're using the existing population of data to infer new information or new knowledge from information we already have. So we can existing components and connections infer new components and connections. And conceptually, this actually is fairly straightforward deductive logic. And there's a very well-known example from logic which runs that Socrates is a man. and man is mortal. Therefore, we can infer or deduce from that Socrates himself must be mortal. So you can kind of take that into a more enterprise architecture. For example, we might have a business process that creates a particular business information object, and we might have another business process that reads the same business information object. Now, that can potentially infer that there's a relationship between those business processes, potentially a message flow between them. So this can be kind of, I guess, what I call deterministic. In other words, we know this is the case, or more probabilistic. We think this is the case. But nonetheless, we can use this to accelerate that population. Just to give you a couple examples of this. Here's the architecture. So the one in the center, this is a big green wiring diagram, actually one from one of our clients with their permission. And so what we've done here is actually they've taken the fact that they have applications, they have interfaces between those applications, and those applications are also mapped to little capabilities describing the logical functions applications perform. We use that to infer from hundreds of application records what the interaction between those functions are. So they might say that the sales system talks to the payment system, the payment system talks to the general ledger. So you infer out logical application pattern from your physical architecture, and then of course from that you can apply onto that your strategic technologies and standards. Third architecture, this is actually a test one, is where we've been using inference to understand how we might migrate application from an on-premise hosting to a cloud-hosted model, and using that to infer via a process, what the cloud hosting, what the consumption of cloud hosting resources would be. Now, inference is interesting when you start to actually, layer deductions on deductions. So, as I said before, if it's probabilistic, then you have to be a little bit wary of layering assumptions on assumptions. But you can actually step through a set of processes, and in fact, you can infer information which you can actually use to populate new architecture views or new architecture artifacts. So, for example, here I have 5 applications. Now, those applications have been rated by their strategic rating. So, in other words, whether we want to keep them or whether to decommission them. And then they've been mapped to logical functions. Kind of, view we can create that actually doesn't require any inference at all. It's actually, we can create an existing application interface diagram simply from understanding the existing data. Now, from that, as per the previous example, we can actually infer out a view of those functions talk to each other. So, iteration pattern. We can then step further and infer. If we apply our strategic technologies to it, we can infer how they, need to talk to each other in our target architecture. And finally, because we understand how those applications relate to those functions, and we understand whether they're strategic or not, we can infer which application needs to migrate to which application. So we can infer a migration path between apps. So what I've talked about so far is kind of about data. So whether it's analysis or whether it's actually structure, whether it's modeling, all we do at this point is creating data, which is elaborating that graph. So at the point we actually need to actually present that out and visualize it. And so we know how to do this. The first to actually automate diagrams. Something we do quite a lot for clients is we actually we automate the production of standard types of diagrams. So in the center of the screen, we have an example of what we call our word according to diagram. And this basically takes it to top to bottom view of an initial application from its high level, from its business processes and the departments that use it, right down to the infrastructure that supports it. What this does is a diagram template, which defines, the layouts and the icons, and then runs an algorithm against it to populate that template. And the bigger of these is these things can be generated, in quantities in a very short period of time. So typically, people might run this process every night and generate hundreds of diagrams every night, which then always be pretty much up to date. Now, the other area of very powerful for visualizing that information is the use of data visualization. And we have our own product in the space called Abacus Intelligence, and I have some screenshots from it. But also, at the risk of kind of being popular with my pre-sales team, there are also a number of libraries out there, open source libraries you can look at. They offer a tremendously rich palette of techniques visualizing your architecture. So I've got some examples here. The Squarify view is what we call a trap, and this is showing applications grouped by regions, and those applications beneath that are actually then colored by whether they're strategic or not. At the bottom, a couple of other views. One I think is called code diagram. Actually, I think it's called hierarchical edge bundling, and the other one is burst diagram. And the big advantage of these visualizations is they're very effective at hiding or revealing complexity because they're interactive. So you can actually click on an area and drill down to the next level. So you can literally navigate from a very high-level view of your architecture right down to the detail. Now, the other big advantage of these visualizations is they're very, very compatible with data in a graph format. Bring all this together. So we've covered some powerful techniques for analyzing, for modeling, for visualizing. At some point, you have to use these and compose them into actually delivering a particular architecture mission. So regardless of what's driving your effort, actually you have a different set of drivers, a different set of business outcomes you need to aim for, and that will drive what you model and how you analyze it. So if you're looking at cloud migration, you're going to be looking at different things from if you're looking at application portfolio management or you're looking at a regulatory compliance project. Each of these is going to be a different profile. But nonetheless, we can start to say how we're going to take things around that loop of modeling and analysis, and where we might use algorithms in that process. So for example, cloud migration, we might start by using an algorithm to actually score the applications to be migrated out to the cloud. We can use inference algorithm to actually start to infer what that cloud architecture might look like. Very important because we then actually need to model the costs using our economic or financial algorithms to actually see whether that's actually going to realize the benefits. Believe it is. And we need to present that information out, so we'll use data visualization to actually push that information out. Now, I would love to say in Abacus that we have a do cloud button, and you can just click it and it all just runs. Kind of end-to-end full cycle is still relatively new for us, but we have implementations in each of these spaces. So I think where we see the market going is that we should effectively be able to compose these algorithmic approaches into delivering one continuous sort of architecture theme. So these things they're not magic. They are very powerful, but there are places where effective algorithms run out of road. So there are the hard questions and there are the hard questions. And so there'll be places where we can help architects and inform their judgment. Places where really the algorithms don't have the potential to do that as much. And I'll give you a couple of examples of that. Is, I guess, what we call the cheesy pizza problem. So transition. How do we decouple from legacy architecture? So say we have a legacy application, and we want to get rid of it, but it still has live business on it. It's still, we need to keep data for the next 5 years. It might be on a technology platform we can't decommission. It might have contractual constraints. So there might be, commercial reasons why we can't easily get rid of it. So, we can model all dependencies. That's what graphs are good at. They can model those different strands of cheese, as it were. But that's not really the challenge. The challenge is figuring out the optimum path through that. So which compromises are you prepared to make to get rid of this thing? So that's a very difficult bit of logic to pursue. And I guess even harder is, the sense of something that architects have to do every day. They actually have to sell their roadmaps. So the algorithms can help us straight how those roadmaps effectively are going to hit the objectives. So whether or not our architectures are getting closer to those organizational objectives or further away. do is actually say, well, those are the right objectives. So we can't help other questions. Should we be going for saving, or should we be going for business growth? Or should we be hanging on to existing customers, focusing on retention, or should we be trying to get new customers in? Those kind of questions are so dependent on things like market factors, brand, internal politics. It's going to be very, very difficult for us to actually architects model that in any meaningful way. What we do believe is that these algorithms are increasingly going to help architects, and they're going to help them answer those hard questions. So there's no certainties. We can't give absolute, definite assurances that the architecture is the right architecture, but we can use analysis to give, the best possible answer, give, the understanding of the enterprise we have at any point in time. So the objective is to kind of provide architects with the best box of tricks, as it were, the best of approaches they can, so that we are, faced with those questions about their roadmaps and the ability to actually deliver those objectives, that in fact do that. We have covered all content. I think we have some time for questions. So Simon, I don't know if we have some questions that wanting answers to, but we've got about 10 minutes, I guess just a little under 10 minutes left. So maybe I'll hand back to you.
Yes, great, Ed. Many thank you for that. Very interesting presentation. Yes, indeed, we do have some questions. So I'll just work my way through them one by one. First of all, Ed, a question from Andy. He says, the algorithms seem very powerful. The presentation has been focused on the modeling of the IT landscape. Could this also be applied to business processes? And he says, for example, if I put in a new system that replaces certain transactions, then work out the likely cost savings.
Yeah, so I mean, one thing I alluded to, but probably didn't pull out strongly enough, is that the kind of algorithms like performance and availability, they actually work equally well across IT and business architectures. So these, to a certain extent, kind of common non-functional properties of your architecture. So it can seem a little bit sort of cold sometimes. We talk about processors, and a processor can be a chip, but it can be a person. It might seem a little bit mechanistic, but the approach does work. So the approach is applicable, and we do have instances of clients use those algorithms equally for both modeling the performance of a business architecture and an IT architecture. And it's kind of coming back to Andy's question, you can do both simultaneously. So you can use the same analysis across both domains and understand really where that boundary needs to fall between your sort of automated and your non-automated enterprise.
Question from James asking, can EA algorithms be industry specific? So he says, for example, healthcare.
Yeah, I think so. I do think so. I mean, I want to drill into what he's got in mind in that space. Models, things like reference models, can definitely be industry specific. So when we actually have a reference model that describes the makeup of our organization, then that is something which is particular to a particular organization. I guess it really comes down to kind of the main areas of analyzing, modeling, and analysis. We understand, for healthcare, what are the particular types of modeling we do which are unique to healthcare, or the types of analysis we need to do which are unique to healthcare. Do we then require to actually to define something which is industry specific, or is it simply a question of applying a more generic algorithm to an industry specific data set, which is a slightly different approach?
Sash asks, how does it fit in changing architectural styles? And he says solutions architecture. I guess he means how does the algorithms fit in changing architectural styles?
Yeah, I don't know. Is that also a question about things like moving towards service orientation or APIs or so as if I've misunderstood the intent of the question, my apologies. I mean, the algorithms are just a pre-canned set of logic. So if, for example, if you have like an existing application landscape, which is very point to point, and in future you want to route your interface through a central, messaging bus or an ESB, or you want to consume interface as APIs instead of bespoke point-to-point interfaces. And, that's effectively something you can build the algorithm. So we talked about, for example, the fact you can not only infer connections, but you can infer components. So one thing you can do is if you have an interface between two applications, you can infer a component along that interface, which could be your ESB. So you'd still have the same endpoints for your messages, but they might then be brokered through a middleware.
Okay, Ed. Chandra asks, one question on the cost. He goes on, since it could be a variable cost, depending on usage mode, some nation would need additional equipment, for example, network repeaters. What is the best practice to perform aggregation and matching that reality, especially future reality?
Well, so modeling variable costs can get very complex, and particularly because we can model variable costs, not just of an individual element, but when you start layering the variable cost of one element, and then how that spreads throughout the wider graph, that get to quite complex, set of kind of cost interactions, I guess you'd call them. Before I can answer the question specifically, I'd probably want to actually have a more detailed question about that. But I guess one of the points I'd make is, yes, you can model variable costs. We can show cost differentials, we can show cost going up, we can show cost going down, we can show spikes in cost. But also, as architects, we also have to model just enough. So one thing I'm cautious about is trying to model cost to the nth degree, and we might be required to answer a high-level cost question. So we need just enough cost modeling to be credible and to provide some confidence in those costs. But you could easily, disappear down a rabbit hole of trying to model every little variation in cost. So I think it would come down to the requirements, the extent to which we need to model those variable costs.
Jason has a question about accurate and completeness of the enterprise's architecture. He asks, if your enterprise is pursuing bimodal, will enterprise architecture algorithms still provide high value?
Wow, question. I think, I'm going to think about that one. So apologies for not answering it here and now.
Yeah, that's fine.
I'll be honest, I'm not sure right now.
That's no problem at all. Question from Liam. How could algorithms help with compliance projects?
Right, okay. From personal experience here of being involved in compliance projects, typically regulators are not as concerned with the performance of architecture. So they're not really concerned with whether you're being cost effective or not, or might be concerned with your service, but they're probably less concerned with that. I think what cases are often most concerned with is transparency. So they want to get a view inside your operations and understand how that works. Now, certainly in the past, I've used inference. We've used inference to do things like understand customer data is stored in applications. So even if we don't have a direct link between our applications and the data part of the model, we can infer that via something else like a process or a function. And then that gives us, a starting point for saying we think these are the critical applications in terms of storing that kind of information. And you have to validate that information, but it's certainly an accelerator. So it's really, I would say probably likely to use things like inference to actually fit in the modeling more than you are to actually analyze the performance of an architecture in a compliance scenario.
Thanks, Ed. Well, we've come to the end of our time. There are a few questions that we haven't managed to get through, Ed, and I will share with you those, and you can take those offline. Before I close, are there any further points you'd just like to make before we end today's presentation?
Not really. I mean, thank you very much for sparing the time. We're always happy to hear from people. We know there's some fantastic work going on out there, people working in the same space. So, if you're interested in knowing more, or if you want to share stuff with us, please just get in contact.
And just final, we had some requests for copies of your slides. Have you thought about sharing your slides and how you may want to do that, Ed?
Certainly do that. I mean, if we have, we'll probably put them on our own website. We can certainly share them back with the open group, and if people want to get in contact directly, also, we're very happy to send out copies.
Excellent. Likewise, everyone will have my email address. If anyone would like a copy of Ed's slides, please feel free to send me an email. I can share those with Ed, and we can help you there. Okay, Ed, many thanks for your time today. Many thanks for everyone who's joined us today. And at this point, I will close today's presentation. Thank you, everyone.
Thank you.